Thanks, John. Thanks for having me. Ohio State has been a place that I don't spend enough time here, but I do try to come very regularly, and it's been a place between the Knowlton School of Architecture and the Wexner Center that's been really important to me. I've been going the last couple of days through things with the students, and going through the lecture, I realized how many touch points there are here. So I thought I would just lay out a couple of basic principles here. That you'll see it when you know it is a play on the Supreme Court Justice's definition of pornography, which is that he'd know it when he saw it. For me, I really think that it's important before one starts thinking about style and forms and shapes to have a set of principles for evaluation and to have some criteria for evaluation. So to do that, I would do two things. The first is to just acknowledge some of the disciplinary qualities in architecture that I'm personally interested in. But I think these are like universal truths. Could be just personal preference. But I think what's unique to architecture, which is very different than, say, industrial design or sculpture or other things where you might be looking at form and shape and style, is that in architecture, not only are we organizing vast assemblies of pieces into very large objects, but we have 2,000 years of history where we celebrate that. So unlike in, say, sculpture, where you might want to have a giant plate of steel which is monolithic and whose joints are invisible, in architecture, we would celebrate the joints and pieces of steel that are assembled. So it's important for me, and I find there are a lot of art historians that miss this fact, to understand that architecture is a discipline with a history and a set of criteria, and it's very distinct from, say, sculpture or industrial design. And the reason I say that is that I think today, primarily because of our medium, we share a lot of design techniques with other industries and other art practices, more than we did 10 years ago. So I think it's important to make these distinctions. Because we build large single things out of a lot of parts and pieces, we have a tradition of holism and of the relationship between a part and a whole. And so proportion and symmetry and harmony, even though they were kind of illegal words or illegal topics to investigate for a long time, I'm personally interested in a lot of these classical ideas and rethinking them. An intricacy between the massing, the interior, the exterior, the relationship of all these things are also very important in architecture. So in architecture, you have a facade where it's our obligation to represent the interior of a building on the exterior of a building, which is not to just say you have to see through the front door, but actually in whether it's ornament, structure, form, materials. It's very important for an architect to represent what's going on inside something on its skin. Again, we're probably the only field that really thinks that way. One of the potential frustrations of our field is that people experience architecture as ambiance and atmosphere. People don't really pay attention to it the way they pay attention to something they're going to sit on or put in their mouth or hang on their wall. And finally, in architecture, we really have to pay a lot of attention to signature. That for an architect, the identity of the design has to transfer across great scales and great building types and contexts. So signature is a little bit of an issue for us as well. Okay, so the qualities of intricacy, of facade, of assembly of different components are unique to our field. What's interesting now is that we're using a digital medium. And I'm not talking about tools here, but actually a medium of expression, which is calculus-based. So whole numbers don't really have any greater value than infinitesimally fractional numbers or numbers to the 7th decimal point in terms of mathematics. So we don't have debates anymore about whether the proportion of 1 to 7 of your nose to your head is better than 1 to 9 of your head to your body, or these kinds of discussions that preoccupied architects a couple hundred years ago. The digital medium thinks in terms of series of variations. It tends to think in a language of curves. Even straight lines are technically curves in the design software that I'm working in and most of the students here are working in. We think in continuous sequences rather than discrete sequences, so it's non-modular. You can get intricacies of scale where a change in one part can change thousands of other parts at the same time in a parametric way. Similarly, you can get all kinds of nested hierarchies where you make a decision about a whole group of the pieces of geometry, and the change of the group will change the part. You can also change the part, and it can go back and change the group. So it's a very different world than drawing a grid and designing on a grid. So the confluence of these new design medium qualities with architectural qualities are what I want to talk about tonight. So the part-to-whole relationship, the fact that these new technologies are a medium of expression. I'll talk a little bit about what is sometimes called evil cuteness, which is a kind of pop culture sensibility coming from Japan. I want to talk a little bit about rethinking minimalism and what that would be today. And I want to talk about generic and genetic form and variations. So that's a kind of big arc of the talk. Now, just as an example of how much things have changed, the term generic was being thrown around a lot, and it tended to mean 10 or 15 years ago the everyday. And I noticed in a text that generic actually was a biological term from the late 19th century about symmetry breaking, and generic was something which was not yet specified. My world was turned upside down when I read this particular biologist's view of symmetry. This is an image from William Bateson from a book he wrote in 1890, and this is the principle of Bateson's rule. The principle is simply this: when you take information away from an organism, it defaults to symmetry. So he went around and studied all of the exceptional cases of growth and found that the exceptions showed more symmetry than the norm. And this led him to invent two terms. One term, generic growth, which is symmetrical growth. The other term, generic growth. He was the person that invented the term genetic. So these are two examples of where you lose information at a thumb. What happens is the hand defaults to either mirroring four fingers where the thumb would be, or it defaults to mirroring another thumb where the regular thumb would be. So Bateson's concept of symmetry was completely opposite of mine, which was that symmetry was the sign of disorder. So if you had uninformed growth, you just simply took an object and mirrored it. And without any information, the way things grow is just by mirroring. The minute they take information, they break the symmetry and change in some different way. So for me, I always thought symmetry was the sign of axial organization and central organization. In fact, for this biologist 120 years ago, symmetry was simply a kind of rote repetition that was the sign of disorganization. So all of these themes like harmony, proportion, rhythm, all of these old Renaissance principles that have been abandoned suddenly get very interesting when you use procedural tools and new kinds of geometries and mathematics. Also, near symmetry, and we talked about this with the students yesterday, I found is the easiest way to get something which looks organically beautiful. And I looked and I found that there are kind of statistical studies of people's faces and when you feel comfortable or uncomfortable with the person. If a person's face is too symmetrical, people feel like they're a little bit off, or a little strange looking. If their faces are too asymmetrical, they also feel like they're off. But everybody's comfortable with the percentage of asymmetry. If you actually do literal symmetry, it becomes very disquieting. And it's an experiment they do where they take people's faces and mirror them identically, and it's true, they look absolutely monstrous. So this idea of symmetry isn't a kind of simple bilateral or axial system. It's much more subtle than that. So I'm going to bounce around a little bit between various scales of things. I'm hoping that the aesthetic principles hold true across the scale. I thought the best example of a way of starting with symmetry, keeping it in the system, and dealing with this new kind of design medium is a set of flatware that I designed not long ago. And we've done a few things with Alessi, and Alberto Alessi said to me when we started this project, you know, the way this should work is, you know, Greg, you should do a spoon. Come to us with a spoon. And based on the design of the spoon, then my team, meaning Alessi's team, will do the fork and the knife and those variations, and then I'll fly back and we'll talk about those. And then based on those, we'll start to do all of the things like serving utensils and cake knives and all that stuff. And I just felt like I've been working with this guy, I thought he was my friend, he doesn't understand me at all, to suggest that I would do a spoon and have him do all the fun variations. So I did this diagram to show him and to get started. Where you can see on the upper left, I designed what biologists would call a primitive, which is the yet to be specified beginning, which has all of the information you need to develop specifically in a lot of different directions. So think of like a fertilized egg or a single cell or something. It's poised to differentiate, but it's not yet specified. So in that thing, I knew that we needed something that could be like a blade, something that could be like tines, something that could be like a bowl. All the elements for the flatware had to be in that primitive before we could start designing. So the primitive, you know, we looked at all these different elements and how to build them into a generic thing. Once we had this generic primitive designed, then we started to play around with it and try to target it towards different utensils of different types. And this is more just exploring how robust our original element would be. At the same time, I started reading Emily Post and all kinds of, trying to get my hands on as much information as I could about flatware and eating utensils and servingware, and found out all these interesting things. Anybody that knows about those things is obvious, but salad forks have 3 tines, dinner forks have 4, and pastry forks have a slot and a bowl to them, and all these things. So that's a pastry fork and a salad fork and a dinner fork, meat serving fork, and these are renderings. But with this digital design tool, which was made not for any industry in particular, but made to take advantage of calculus in terms of geometry. So animators like this. I think industrial designers and architects haven't really tapped into the design potential of these calculus-based tools, but what they're very good at is blending and mixing variables together is a design medium. So we have a lot of kind of robots and things in the office. Like this is 3D printed, meaning there's a machine like a little oven that prints plastics in the office. So we printed plastic models. We then went to a special place that can print in steel, and we printed these tool steel models and then silver plated them to start to see what the flatware would look like. And when I went to Alessi with this stuff, you know, they're like, wow, I haven't seen a cream chip bacon fork for a long time. So they were able to identify what all these things were. And the whole design process is about designing something that has a very robust ability to mutate and change in a controlled design way. And it's not like we're inputting information into a black box that makes decisions. I'm just talking about a very cool pencil for me to design with. And then learning about all these different elements. And so in the end, we did the conventional 52-piece flatware set that has all berry knives and dessert serving spoons and ladles and all that stuff in the set. Now, what's important for me is that there was no original spoon here. There wasn't one piece that got deformed into all the others, which is the classical way of thinking about design variation. Here they were all designed together, and they're all a family. So every one of them is different, but the whole family belongs to a group set. And this kind of an approach to design, where you're not designing the perfect thing, but you're designing tens or hundreds or thousands or hundreds of thousands of unique objects, all at the same time, all equally perfect and functional and beautiful. This is totally possible with software, and it's, you know, also has been possible in terms of manufacturing for a long time. We just haven't been able to design for it. So this idea of a family of objects has persisted, and it's drawn me a little bit into industrial design projects. But again, I would argue only an architect would do something like this. You know, this is like the mullions in a curtain wall, where every mullion is different, but they all make one thing. Only from architecture would you have the idea to design all these things in a family that all belong together, but are all different. But it's very much like how we think about parts of a building in a whole. This was a project that started my relationship with Alessi, which are these teapots. And I won't go into this, but you know, here we designed a little bit over 30,000 unique coffee pots and teapots. And the way we did it is we designed 8 compatible curves, which you see in this graph, and lofted surfaces between these curves, and worked on that relationship of curve to curve until we were confident that we could produce always the same volume of coffee pot and always ergonomically functional pots and always beautiful Greg Lynn designed coffee pots. And to do that, we, you know, did renderings. You know, I told the students, I said, these are wrong. We had a discussion about it. We all agreed they're wrong. These are right. And built, say, hundreds, you know, less than 1,000, probably more than 200 models to test them. And once we'd gone through those several hundred models, I could say with confidence, I'd sign every one of these 30,000 pots. They're all equally beautiful. That same approach translates into the building scale. This is a housing project in Valencia, Spain, where all of the apartment units are subtly different, and the subtle difference adds up to produce a whole which is dynamic. These are the very first studies of the units. We mold the units by these negative voids that cut between them, and these are some very early studies. What happens in this project is we rationalize this variation in a very particular way. So here in the plans you can see a typical floor level where 6 of these units vary. There's some 2-bedroom units, some 1-bedroom units. These are the kind of floor-by-floor variations. And we rationalize these plates now, the floor plates, where there are these super components, is what you call them, but very large-scale factory-built elements. This is not the color of the building. This is a diagram to explain to the builder how we're rationalizing the system. So there are 4 kinds of cladding, all of which are, each one of the 4 is different, but they're all mass producible. And they can be rotated along a central axis. And when combined, they give you these different voids in between the blocks. These are the components. We have, you can see in the top and bottom, half components, the only variations in them. And when you assemble them all up, you get an effect like this in the drawing, which in the drawing was great. We then did renderings where it started to go very Flintstone in the sense of these deep punched openings through a solid, worse, and built a model to check. It was, yeah, bad. So I started to think about how to take the quality of the window as a punched opening off the wall, and thought about doing some kind of a reflective skin where we could put reflective film on the glass and have a reflective skin. My wife, Sylvia Lavin, has been working on late 60s and 70s architecture of discotheques in Europe and Italy, and I was thinking, well, it could be like a diffracting disco ball. It's also perfect in, it sits in an orange grove, this building in Spain. So that it would be great contrast with nature to do that. But instead of just cladding it in metal, we interpreted this image as 6 different colors of panel. Because at the scale of the building, to take advantage of the fact that it's made out of different parts and pieces, it seemed more sensible to treat the parts differently rather than to rely on a material to do that. So, let me see, this laser pointer's tired, but it's not going to work. So this image is a model which we built out of 6 different kinds of metal and glass. So there's 7 materials here. If you look, okay, I can use the mouse. Never mind. Can you see the mouse? Okay, so the different materials are, it's all aluminum. We just anodize the aluminum differently. So there's white anodized aluminum, there's gold anodized aluminum, there's copper anodized aluminum, there's brush finish clear coated aluminum, there's polished clear aluminum, and there's black anodized aluminum. And in addition, there's mirror finished glass. So there's 6 different finishes here to generate the dazzle effect of a disco ball, rather than just covering it with, say, polished aluminum. So here in the image, you can see the kind of color coding of all the different metal finishes, and it's done as if it's a rendering. So the white is from the sun, is from arbitrary position of the sun. The dark is in shade or in shadow, and then the other variations pick up the form. So also the color of the material accentuates the form. But it's an approach to the building which celebrates the fact that it's made out of a lot of parts and renders all those parts as if it was a whole. I wouldn't have thought of it if I didn't have rendering software, by the way. I mean, if you weren't assigning texture maps to software, I really doubt I would have had this idea. I mean, you could have done it otherwise. But. Okay, so also in terms of, here's a kind of familiar print. Although, yeah, that's it. So this is the Predator that I did with Fabian Marcaccio, who's a painter. And Fabian was starting to paint these 3-dimensional paintings that were coming off the wall and into the room. And so we got together and said, let's make a giant, hollow, occupiable plastic painting. It's about 100 feet long. And I don't know why Sherry said, yeah, that sounds like a good idea, but we did that. And it was where I bought a large robotic CNC mill for my office to make all these panels, and it's made out of a couple hundred unique panels that are molded on custom molds. And the process was to take a piece of a shape of geometry and translate it to the movement of a tool path, like a drill. And usually you do that so it's smooth, but with Fabian we started playing around with how we translated the geometry into the tool path, and we came up with all of these painterly ribbons and effects and textures, even to make kind of brush strokes. This is a detail of an interior wall at the Uniserv headquarters in Los Angeles, where I did the same thing. So the process of translating a piece of abstract geometry into the physical movement of a tool gives you this new texture and pattern and articulation. Same thing with this detail of the Pretty Good Life showroom in Stockholm, Sweden, where we use that also to integrate these removable posts for the shelving. But this translation from abstract geometry to machine language gave us the opportunity for a new language. This is the Netherlands Architecture Institute. So that kind of pattern and texture has been interesting to me. Also, nothing special about frogs, but it's just a good example of a pattern which is intricate to a form. So you can see the pattern changes where the form changes. And that kind of thing is very different than, let's say, Robert Venturi or Jean Nouvel decaling a form with a texture. This is a texture that's intricate to the shape and accentuates it. So that kind of approach to color and texture and pattern is also something I've been playing around with. It's too late for me to talk to you about the difference between calculus and partial differential equations in terms of design. But I would say, for all of the students that are using subdivision surfaces out there, that what you're starting to use is a partial differential equation approach to design, where you start with lines and points and progressively smooth them until they approach curves. Now, for the last 10 years, I've been designing with curves and then translating those curves into lines, like the surfaces of those objects which are tooled start as infinitesimally complex surfaces that are defined in calculus and get translated into line movements of a tool. They have point coordinates for where you attach them. This other approach, which is becoming more and more dominant, is to start with simpler lines and smooth them where you need them and can. So this is a pavilion that Tom Krenz and the TDIC in Abu Dhabi had commissioned on an island called Saadiyat Cultural Island in Abu Dhabi. And it's an artificial island built in the sea. It's got, this is Nouvel's Louvre, this is Zaha Hadid's Music Center, this was Ondo's Maritime Museum, which I think moved, and then Frank Gehry's doing a Guggenheim Museum out here on the point. Now, connecting these up is a canal with 19 pavilions arrayed in it. And I'm doing one of those pavilions. It happens to be one that's a bridge across two different sites. The only mandate that all of us had from Tom is that these pavilions would be used for single artist shows of living contemporary artists, and they had to be able to accommodate the largest work of art being done by a living contemporary artist, as well as a lot of small pieces of art by all living contemporary artists. So obviously you wanted a high degree of flexibility. The approach to it that I took was very much inspired by the squinches and transitions of rectangular volumes into domes and vaults in Islamic architecture in general, as well as specifically some of these Iranian bathhouses, which do this in a very intricate way in terms of apertures and openings. So here you can see a detail of a model of the ceiling that we're working on, where we have linear wall divisions between galleries, which exist as a kind of uniform plane of a soffit. So you can build removable walls up to that point. And then as they vault up, they potentially get smoother and smoother until they make a kind of oculus. The other thing that's really driving this project is that it's a kind of art bridge. So there's a gallery bridge that spans the canal. And we're folding that horizontal bridge into a vertical chimney, which is typically used in the Middle East for passive cooling. So you superheat these chimneys, so you get them really hot, and the air moves vertically through them, and you can start to draw cooler air from the ground through the building and generate breeze inside the building and airflow. So here, the way that works, when you see the site, the first site is here, and it wraps around out to the Guggenheim out here. You can see that in this roof plan, how these divisions of walls progressively get their corners cut off using an algorithm called Chaikin's algorithm. So they get cut once, so they're smoother. So there's twice as many line segments here. They get cut again, and they get cut again. So these lines progressively become more and more like circles. Here you can see the divisions looking up into the gallery spaces. Here's just a diagram showing how this glass-covered bridge gallery is here, so you can get a big, vast, continuous gallery space across the canal in this scenario, or you can build these temporary walls up to that 9-meter high soffit and be able to close it up into 23 different galleries. With Tom Sachs stuff in it, because Tom does really big stuff. And then the glass bridge gallery here. And here you can see the way those solar chimneys work. So there are long glass-covered ramps that run along the water and are open on one side. So they'll pull some of the evaporatively cooled water off this walkway. And then these are the chimneys that'll get super hot, like 150, 180 degrees in the summertime. And these will suck all the cool air from the water through the building and up out the top of the building. And you can see also the transition from these facets, getting more and more faceted until they hit these oculi, and the multiple oculi in the gallery, a little bit like those Iranian bowls. And it's approached with a ramp up here and a ramp up there, and then an escalator down there and an escalator down over there. So everybody pools into 2 entries at each end of the bridge. And the landscape is pretty schematic right now, but takes on some of the form of massing. The BMW Design Center, which I'm not going to go into so much. The approach of surfaces that I've been talking about so far has been about articulation and producing detail. I got forced into a marriage with Hedi Slimane from Christian Dior on a project for Visionaire, and Hedi Slimane is kind of the apex cool gray minimalist out there. And in this collaboration, I got interested in using surfaces for not maximal effects of articulation, but also minimal effects. This is the project for Visionaire magazine with Hedi Slimane, and Hedi got on the phone with me, and we were introduced, and he said, I love your stuff. I really want you to do something special here. Could you just make sure that it's a cool gray number 3 box with no articulation and no hinges or clasps, and then just knock yourself out. And so I thought, well, I guess I know who's in charge. But so anyway, and the magazine, the Visionaire magazine, was already designed and printed. So this case that we designed for it, I decided to use the surface of the inside of the case to be the hinges, to be the clasp, to remove all the stuff that Hedi wanted removed, but then to do it with some kind of surfacing qualities. So you can see there are these teeth that run along the sides of the case that interlock, and there are also these larger indentations that interlock, and then there are the ridges that the magazine rests on. So the magazine floats on this surface, And the only way to get it open and closed is to lift it perfectly vertically up and down. Otherwise, you don't need hinges and you don't need a clasp. So I was able to get rid of all of the mechanisms of a case by modulating the surface of the interior. So swallowing up details with surfaces has been a preoccupation. This is the Alessi coffee cup, where Alberto said, no matter what you do, you have to put a handle on this because architects never put handles on their cups and people always burn their hands. And you have to have a saucer so you don't burn the table when you set it down and you don't make a stain on the table. So this cup works that it's handles everywhere. So inside here, there's a kind of cylindrical cup on the inside, and then on the outside, it has this shape, which is great to grab, and it has the ridges on it, which are kind of like the memory of the handles, and also like the texture of those walls that comes from the milling machine. And we opposed all the surfaces, so on every side of the cup, there's like a male side and a female side, or female-male, however you want to spoon together, or male sides. But these things all nest together and interlock. So when you put them on your table, you can start to make these crazy arrangements and little cities out of coffee cups. They'll all lock together. And because the inside has an air pocket with the outside, you can put steaming hot liquids in here and always grab it with your hand. But I didn't have to use a handle and didn't have to have a saucer. So this is a case where a kind of surface approach takes care of extra elements. This is that coffee set I told you about. These are coffee pots in titanium, and inside here is a flask which is floated between a bed of silicone so you can grab it, and it sits on a tray which is reversible. So when the coffee and teapot are full of hot coffee and tea, you stack them on this tray and the tray rests on these ridges. When they're clean and empty, you flip the tray over and those ridges interlock with the back side of the coffee pots. So it lays open like a flower on a coffee table when you're displaying it, and then you spin it around and stack them up when you're using it. These are just images of how it's produced. Same thing with this ravioli chair for Vitra, where it's got a hard surface and a soft surface, and the soft surface is knitted with a three-dimensional knitting machine, so that's why it's got half the number of knots here that it has, say, there. And the arms, the back, and the seat are all taken care of with one bucket, and the legs are all taken care of with a kind of hard shell. So it's a two-part, there's more than two pieces to this chair, but it solves the four legs, the arms, the back, and the seat with two surfaces, a soft surface and a hard surface. And it's a chair. It's not an art chair. We got asked to do an art chair. So the art chair version is gold-plated and chrome-plated, and has alpaca fur and hydrogen fur on it. So it's even harder and softer. Same thing with these plates. This is the Chaikin's algorithm that blends together bowls and plates and cups together. Material that I've gotten very interested in is plastics. The plastics of the Predator here at the Wexner was one kind of plastics. This is a show at Vitra with these plastic bubble cabinets with my robot collection. Well, unfortunately for my family, one very small fraction of my robot collection. And these fiberglass luminous ceilings that we did. So the base of the Vitra chairs is fiberglass that's been painted. This is thermoformed plastic. This is also fiberglass molded. And so, and I don't know why these are here, except that's a killer whale in my neighborhood that we took a picture of. So I'm very inspired by large sea life, and I spend a lot of time on a giant piece of plastic in the middle of the ocean. So when I got asked to do this house on the Pacific Ocean, I really thought about how could I turn this into a boat in some ways, or how could I build a boat in this thing? How could I use plastics in the house. I also wanted to focus on the interior volumes that were plastic in the way the walls were all molded. Now, this house it's a block, which I know is a shock, but we maximized every 1/16 of an inch we could to get a single family onto this tiny little lot that was meant for a bungalow. So this perimeter was the maximum perimeter we could take by the city. And so then the work really started to develop these interior surfaces, and it's like a townhouse on the sidewalls. I mean, there's some stuff going on with them, but it's primarily focused on the inside of the house. Like the Vitra chair, which sucked the legs and the seat into a surface, there's really, the wall surfaces don't make rooms. I mean, it's a little bit like an Adolf Loos approach, where the wall sucks out and makes a pocket, and then disappears back and makes a nook, like a breakfast nook. This wall sucks the fireplace into the wall, and then pulls around to make a powder room, and then develops into the floors fold up and make kitchen islands and tables, and the ceiling folds down and becomes a giant boat-like light. So all the surfaces are folding around. Upstairs, all the bathroom vanity and sinks and cabinets and powder nooks all also get sucked into a single surface. So, and a lot of this stuff uses plastic. I'll show you. The walls also have this stainless steel reglet that swallows up all the windows. So the windows kind of split out of this metal rail and pinch to disappear again. This is the very kind of first rendering where you can see this fiberglass luminous ceiling that folds out of the ceiling, the fireplace that sucks into the walls that curve around to make the rooms. And because of the frontal nature of the house, every time we're in this orientation, we always have a grid, like an eggshell grid, egg crate grid like this. Every time we're in that orientation, we fold the walls, and where we need to, we slice them. There's all these slices around, you'll see. This is from a couple of weeks ago. You can see that fireplace with a slice in it. You'll see this wall has a grid in it. The way the walls are made is with a kind of egg crate framing that's cut by a laser. This laser is 30 years old, so I could have been doing this 30 years ago. Like when I was 14 years old, I could have been building these funny shapes. Just for everybody that thinks the construction industry is so far behind and we're so far ahead as designers, it's absolutely the other way around. So we cut all the components. Also, we took a look and we found out we wasted less wood by laser cutting our framing than we would have if we bought a bunch of sticks and cut them to length. So this kind of customization is also very efficient. I have no idea, honestly, about the fumes. I mean, it's done in the state of California, so slicing glue with a laser can't be that toxic, but I wasn't there. But anyway, I don't know if it's sustainable or not. I know it's not wasteful. We actually put this wall together. We got rid of the job captain who wasn't letting us get anywhere near it, and the owner of the contracting company and the two clients and myself went over at lunch and unwrapped all these pieces which had laser cut numbers on them and popped the wall together ourselves. And that's just to say that unskilled labor can do very precise things when you get machines involved. And also, very skilled labor, like a guy that's been plastering for 40 years, D, came in and did the plaster finish on the whole interior. So what was nice about this is there weren't a lot of laborers with hammers whacking around on things. There were pieces that came in and got fit together precisely, and then there were really expert artisans that came in and worked on them. So that's kind of the finished surfaces. We spent a lot of time figuring out the spacing of all that egg crating, so we didn't get these celluloid walls Also, for anybody that wants to do this, don't ever let somebody with sandpaper get near your plaster finishes. Because I know, I've seen a lot of examples where you try to get the shape roughly and then rely on people with sandpaper, and they come and sand dimples all over your surfaces. So this was all done with, you can't really see it, but we also couldn't laser cut it because it was a ragged edge, but water jet cut custom trowels even for this guy. So he could go in, and the last thing that ever hit the surface was his trowel. So different pieces of the walls with that plaster. The luminous ceiling lit up with cold cathode lights. The windows are all, to say stock is too extreme, but they're 15-year guaranteed Pella windows manufactured by Pella. If you just put a box under this thing, you call it a cathedral window. And so we just spun the top of the cathedral window around and pinched them at a point. And the windows are all fixed at the curves and operable where they turn the corner in that orthogonal view. So the lantern was made up in Sonoma County by Bill Chrysler, most of whose work is in the building industry now. He used to be a boat builder. And he cut foam molds, coated the foam molds in aluminum foil, then cast fiberglass panels off those aluminum foil molds, assembled them up in Sonoma on a template. We had an identical copy of the template that we hung on the ceiling. And then they got shipped down and installed. Not supposed to show that. In the kitchen, we started using a lot of corian, which is a solid core plastic. And DuPont worked with us on a molding technique. And you can see this is the kitchen island turned upside down, but it's going to sit right here. And all of the handles and everything are also custom molded in corian. A similar solid surface material for all the built-in shelves. This is on the inside of that closet. They're scribed up against the inside plaster surface. Same thing in the dining room. This color core up against the curved wall. Then in the bathrooms, like I said, we took the linen cabinet, which is here, the vanity, the mirrors with the cabinets behind, the sinks, and molded them all into a surface. And also, you'll see this becomes a rendering in mosaic tile in the bathroom. And then slice that surface like we did with the fireplace. Same thing with the breakfast table, with the kitchen island. You can see those two table elements in the factory. Pieces of the sink for the kids' room, all molded together in this monolithic material. The linen closet. And then installed, the tile is all a rendering, like you can see it there better, is all taken from a rendering of this wall surface. So the graphic quality of the tile also mirrors the physical quality of these corian molded surfaces. Same thing with the bed, we're doing in bamboo. I don't have a picture of that yet, but the upstairs it's all bamboo floors, and all the beds kind of mold out of the bamboo floors. The light, Kraken light, which is 3D printed light that goes over the dining room table. So all this plastic stuff, the corian's plastic. The bamboo, even though we like to think it's kind of healthy bamboo, it's all plastic pretty much. So the luminous ceiling is all plastic. It's a very plastic house. The person who wants a plastic house more than anybody is my wife, Lynn. And I'm going to show you the design for our house, which I've been playing around with and not getting anywhere on. But certain things from it have come to fruition. And again, they're more plastics. So for the house, there are a few inspirations. One is this house by Lynn, which cantilevers over a hill and in the center of this cantilever carves out a courtyard. And it's a really amazing house because you get this floating courtyard, and when you're in the house, you get an amazing view out from the hill, but you also get an amazing view down and out through your house down the hill. So this idea of punching courtyards through a suspended house was kind of the first place we started. You can see the lot is a pie-shaped lot, again with very limited zoning, but by lifting the whole house in the air. We also have to park 3 cars on this lot with a 8.5-foot dimension at one end of the site. So this whole thing under here is a parking lot, which, because we don't have that many cars, we live in. So, and light gets brought into that through these courtyards, which are punched through the volume of the house. The second thing are these filleted columns of Wright's Johnson wax, where the columns mold and disappear into the ceiling. You know, never noticed, but a lot like some of those courtyard things, or some of the things in the Bloom House. And finally, the structural idea is that instead of having a truss built out of columns with a beam, the truss is a continuous rolled tube of steel that runs down the entire length of the house, and is expressed on the facade of the house and also on the roof of the house. So they won't be beams that are bent the hard way like this. They'll actually be tubes, like 8-inch tubes of varying thickness. And we modeled these all with Gary Technologies software, with the CATIA. And even though it doesn't matter, I found, we made them all whole number radii, and they're all linked together. So if you move any one part, you can see it moves the whole section. So and these are also set up so that they're offset by 8 inches so that they can be rigidly welded to each other to give you stiffness in the direction of the truss. And I developed this truss with Klaus Bollinger, so called the Bollinger truss. And you can see how this tube wraps around and offsets and weaves through itself to get its rigidity and plane. For those dimensions. For the articulation of the interior of the house, I start with those loops and connect from the north side of the house to the south side of the house, from loop to loop. And that gives us these kind of courtyards that pinch where they fold through each other. The north side of the house, we use some kind of translucent curtain wall system. There's a channel, glass channel here. And you'll see the truss looping through the house through the north facade. And then on the south facade, it's opaque, and you get these large light wells which bring light down into the courtyard below. In the summertime, it's kind of limited right here because it's set directly south. In the winter, it'll get a lot deeper into the courtyard. What happened with the house is we've got kids. They're not so young anymore, but they're 7 and 9. And for a while, we had all these giant pieces of plastic, rotomolded plastic around the house, like rocking horses, sleds, things to tow behind the boat, playhouses, all single objects made in the rotomolded plastic machine, which is you make a mold and you stick the mold in an oven and get it hot, and you pour plastic pellets, and the mold tumbles around and the plastic melts on the walls, and you pop it out. It's slow, it takes like 10 minutes apart, but very, very cheap for tooling. So they make kids' toys out of it, and it's UV stable, recyclable and recycled. Just seemed like a great building material. So I said, to Sylvia, why don't we take the kids' toys and start collecting toys, and I'll scan them, we'll compose them in the computer, I'll use the robot to cut the joints between them, and we'll glue them together, and we'll build all the interior walls out of recycled toys. So, who knew, but somebody called Andreas Frosch from a company called Candlelight. He was bidding on some of the elements in that other house I showed you. He saw this model and he said, hey, what are those? And I said, they're plastic bricks of recycled toys. He said, we got to make that a product. So we came up with this blob wall system where instead of recycling the toys, we just invented our own brick. And that's the brick we invented. It's a hollow plastic brick. You can see it's about 3 feet in a triangle, and it's made with 3 lobes. So one lobe can kind of nest in between the other 2, or you can rotate it and spin it to start to get really bumpy, rusticated facades, like in a Renaissance palazzo. We take these bricks and array them in patterns across surfaces, and we find the points of intersection. So each brick will usually intersect between 4 other bricks, sometimes more. And we take this line and program a robot with that, and we put the brick on a jig, and the robot cuts away the part we don't want. We recycle that and assemble the bricks one on top of another. So it's rethinking what a brick is, or rethinking what masonry is. So instead of a modular element that gets stacked with mortar, this is a very precise brick which interlocks with its neighbors. And instead of being a very heavy, fired masonry system, this is a lightweight, easily transportable system that's hollow. That's the robot. I can show you a video of the robot cutting up some of these things. It's pretty fun. But this is the robot that cuts the blob wall bricks. You can see here how they look when they're not yet assembled. This is the kind of early one we did for Mocha. That's it in Mocha. This is one we did that actually just sold in Phillips Decoury. I keep trying to make things that the populace wants, but it doesn't work. But this system, although we invented it for the house, the idea is use it in hotel lobbies, use it as a pool cabana, use it as a garden wall, use it as a room divider. We've sold now 6 of them. 2 of them in the art world and 4 of them for just people. This is us driving it around LA, on my favorite building. This is where we decided it would be better outside than inside. And then this is a giant one we built at SciArt, and I kind of didn't know what form to make, so we just made a giant blob wall brick. And for the Biennale in Venice recently, we were going to send some blob wall systems, and actually decided that I would go back to the first idea of doing this with recycled toys. So we took toys from 5 different manufacturers, scanned them, the little dots are for the scanner, scanned these things in the computer, built a surface mesh out of them, arrayed them in a pattern, put them on the robot, cut them up, it worked out. Poor alligator. And started to assemble them into furniture. So, shelf, table, side tables, bench table, that's in Venice.